Mapping every possible outcome of a complex sequence by hand reveals how aggressively these spaces expand. The matrix quickly exceeds our ability to track manually. Taming these possibility spaces requires a single mathematical axiom that serves as the foundation for the entire field. This is the fundamental principle of counting, the AND rule. If task A takes m ways and task B takes n ways, their sequence is m times n. Contrastingly, the OR rule below applies when choosing between options, resulting in a sum. Every formula we use, permutations, combinations, and divisors, serves as a compressed notation for this same process of sequential multiplication. Combinatorics functions as a precise architectural system built entirely on the recursive application of this multiplicative principle. We can now apply this multiplicative rule to a closed, finite system of n distinct items. This creates the factorial, denoted by n and an exclamation mark. Conceptually, a factorial represents a cascading chain of dependent multiplicative choices. Placing n objects into n slots gives us n choices for the first position. Once that object is placed, it is removed from the pool, leaving n-1 choices for the second slot, n-2 for the third, and so on. The formal expansion reflects this physical reduction. N factorial equals n times every subsequent smaller integer down to 1. This logic explains why 0 factorial equals 1. There is exactly one way to arrange 0 items, the existence of the empty set itself. The factorial represents the absolute maximum, unconstrained structural ceiling of a state space. Advanced formulas simply apply constraints to cut this number down. Our first constraint is capacity. Consider a scenario where we have n items, but only r available spaces to fill. Arranging a specific subset where order is significant is defined as a permutation. The formula n key r is n factorial divided by n minus r factorial. The numerator, n factorial, establishes the baseline as if we were arranging every item in the set. The denominator, n minus r factorial, operates as a deliberate mathematical tool to halt the factorial sequence the moment our r slots are filled. It shears off the unused items from the calculation. Division here serves as the mechanism for severing unneeded sequential branches from the possibility tree. A second constraint involves indistinguishable items. The state space changes when the core elements of the set are no longer unique. The Alabad case study demonstrates internal redundancy. We must arrange the letters of this specific word. With 9 letters total, the baseline is 9 factorial. But because A appears 4 times and L appears twice, this baseline is a massive overcount. Swapping the position of 2 identical A's does not change the physical arrangement of the word. These swaps generate identical configurations that must be accounted for. We correct this by dividing the total system of 9 factorial by the internal permutations of the repeating elements, 4 factorial and 2 factorial. In advanced combinatorics, division serves to eliminate redundancy, collapsing identical configurations into a single unique state. This exact same logic of redundancy naturally extends outward from internal repeating elements into repeating symmetrical spatial geometries. Seating n distinct people in a circle creates redundancy because rotating the entire arrangement by 1 seat does not change the relative positions of the people. To break this symmetry, we mathematically fix one person in place. This absolute anchor reduces the circular arrangement to a linear one, resulting in n-1 factorial ways. A bead or necklace adds one final constraint, shown here as dividing by 2. A physical necklace can be flipped over in 3-dimensional space. Because a clockwise arrangement and its counterclockwise reflection are indistinguishable once flipped, we divide the possibilities in half. Recognizing and mathematically dividing out spatial symmetries is a requirement for accurate discrete logic. The final constraint involves cases where we care about the selection of items but disregard their internal order. This is a combination, or NCR. As shown in the relation here, it is tied directly to the permutation formula. A combination is a permutation where the internal redundancy of the chosen subset has been removed. Dividing a completed permutation by r factorial mathematically declares that all internal reorderings of those chosen items are identical. The sequence is removed, leaving only the group. Combinations are functionally equivalent to permutations that have been stripped of internal sequence. Identifying choices and managing constraints allows us to calculate the internal structure of large integers. This combinatorial approach provides a method for finding the total number of integer factors for any given value. A prime-factored number represents a pool of components. Identifying a factor is a combinatorial choice of which prime building blocks to include in a subset. Choosing how many times to include a prime A gives us x plus 1 independent choices, because we can include anywhere from 0 to x copies. This mirrors the independent choice bins established at the beginning of the video. Multiplying these independent choices together using x plus 1 times y plus 1 resolves the total number of factors. From arranging letters to flipping necklaces to counting factors of large integers, every combinatorial equation derives from the fundamental principle of counting, refined by the logic of division.